using high-performance classical computers. And so we use quantum computers to effectively simulate the electronic structure of something like that. And that could inform potentially how we would build a catalyst that would efficiently synthesize that. Another application is, you think about like carbon dioxide. You can actually take carbon dioxide and make methanol, which is a simple fuel. But the energy required to take something like CO2 and turn it into a fuel would require more energy than the fuel would actually yield. It's not necessarily a net positive reaction. But there are catalysts out there that can efficiently synthesize CO2 into methanol. So we were able to understand, I guess, the underlying quantum mechanical principles of something like that and effectively synthesize those things. I think you would see a whole trillions of dollars, I think, in just the simulations field alone that would be unlocked by quantum computing. Unclear when that is, but I think that's more valuable than getting your S's emails and stuff.
Okay, so I want to move on to the next question. The question is this: what do you think? What do you expect to be coming over the next 5 years in the field of quantum computing? Is there any major milestone or achievement that you expect to happen in this time frame?
Well, I'm very much hoping that we will have built a very large quantum computer within 5 years. Like, we're throwing everything at that. I think within the field itself, just a better understanding of some of the algorithms. Yes, I think there's this hope, but right now we don't have concrete evidence for it that even with a small-scale quantum system, there's really this asymmetry that it's difficult to simulate a small-scale quantum system, but we can't seem to take those small-scale systems and do very useful things with them. And I think that we really have to understand this asymmetry, and the hope is that doing that might bring quantum computing much faster. But I've been around a long time in quantum computing, more than 20 years, and very smart people have worked on some of these problems, and I think that it's great that there's more people working on it, but it's difficult stuff. And one of the big difficulties is that we don't have simple programming languages that some kid sitting on the equivalent of a Commodore 64 can work out how to program. So there's, I think there's sort of challenges for the field like that. And one of my passions and one of the reasons I wrote that book is to try and get even younger people learning quantum theory. I think that it's possible for high school students, even intermediate high school students, to learn it. That will change some of their understanding about, the way the world works, that old people like me, can't come up with these breakthroughs, but hopefully some young people out there will.
The one in the back first, and then then I'll go. You're the third.
So
sorry.
Yes, when you were talking about the large scale of quantum computers, I was wondering, is there options of parallelizing computations, so breaking up larger systems, molecules, into smaller components, recombining them?
I think you need to
Isaac probably can answer that better than you.
Sure. Maybe I can take this one. So generally speaking, no. Usually,
Should you repeat the question?
Right. So the question is, given, if I understood it correctly, given a problem, is there a way to break it down and parallelize it in a quantum computer? Generally speaking, no. If this was possible for a completely general problem, you would in fact you can come up with a conclusion that you can always efficiently simulate a quantum computer. So if you believe that quantum computer has a power that is untapped by the classical computer, for general purpose algorithms, this will not work. Having said that, maybe there are special class of algorithms for which this approach might work. But whether that, we don't know such algorithms yet.
So I have a question for Terry. What's the degree of freedom you're exploiting with your photons, and also what's the error correcting code?
Those are great questions. So we use just the spatial modes. So we essentially cut 2 channels in the silicon. And if the photon is in channel 1, that's our qubit 0. If it's in channel 2, that's our qubit 1. And a superposition, the photon is literally just in a superposition of being in one or the other. And to create a superposition, it's actually very simple. Like our quantum part of our architecture is incredibly simple. It's just we etch the silicon, we bring the channels a little bit closer together. There's a tunneling phenomenon between the photons, we bring them apart. Those are extremely precise, high fidelity operations. They are not our concerns. The error correcting codes, this is a very good and deep question, and it's difficult to give an answer without being sure what level of expertise you have. But we use topological error correction, which was invented for condensed matter systems, which are all interacting and doing nasty, noisy things with each other. And there was this hope that, like, oh, we could use topological degrees of freedom, which are really difficult to explain in one degree, but it's sort of like very delocalized degrees of freedom to encode the quantum information. We use those same states, even though our photons are not interacting with each other. So we kind of get the advantage of those codes, which are extremely nice, and there's multiple different ones that we are optimizing over, without sort of having to deal with the nastiness of, you saw like Microsoft want to build Majoranas, they want to build like kind of a topological qubit. Many people have looked at this kind of thing. I think it's very difficult. So we're sort of using these topological codes, including ones that are not very natural for a 2D system.
Then maybe a short follow-up. What's your current quality of improvement?
So our current, like the way I would like to say this is, to what I consider a sensible metric, we have 0 qubits right now. I don't think we should expect to have any qubits for a long time. You know, we are really following a very different path. We're not going 1 qubit to the next, to the next. If you put 20 photons on that wafer that we have, that's the equivalent of 150 qubits in terms of the dimension of the Hilbert space. It's a completely stupid, meaningless number that would just annoy people if we built that and said, oh, this is 150. Right? So it's just not the path. You know, it's like going to San Francisco and measuring your progress by the buildings. It doesn't work if you're going up too early.
Okay, thank you.
Yes. Yeah, this is a
Can you
quick.
repeat the question?
Yeah, so the question is, there's this impression in the press that quantum computing is exponentially faster than classical computer on any computational tasks. However, your guess is that for NP-hard problems, this is unlikely to be the case, right? And this is the consensus, yes. So just to reiterate, the class of problems for which we know there's a quantum speedup is very specific. Factoring is one of them, but yes. So you're right about that. I will one last question, and then I'll move on to the next one.
Simple question. The photon behaviors similar to electron in very low temperature. In photon, similar to electron in very low temperature.
No, so these photons basically do nothing. Like, they're not like electrons or pieces of matter or whatever. They don't care about the temperature. Our photons is like, this is why there's sort of no decoherence. As far as they're concerned, the universe is 0 temperature. It's so far, you know, it's unmeasurable, the temperature, basically.
I just wanted to follow up on the parallelization question. Couldn't you parallelize if you had a fully quantum memory communication? Like no loss of coherence as you transmit and store it?
The answer is yes, but you need an ability to communicate between different modules coherently.
Well, that's what the quantum networking guys are.
Yes, so if that is possible, of course there will be this bottleneck. I mean, there's this bottleneck in the establishing a correlation between these different modules. which, if you have sufficiently many modules, will not be a problem. But my interpretation of to defend myself, my interpretation of the question was that if you have disconnected quantum components, whether you can get a speed up, to which the answer is no. Okay, so I want to go on to the next question. So suppose we go far into the future, let's say like 100 years from now, so that we know for a fact that there's going to be like a super large scale quantum computer, and like everybody's using it. Like, which industry do you think will be affected the most?
Maybe I can answer that question. And I think I'll kind of answer one of the earlier questions too about the someone was referencing the RSA hacking kind of thing. But if in the event that there are a lot of qubits, a lot of logical qubits that we can use, I think one of the key things is definitely going to be factoring for cryptography and cracking RSA. Right now, I think, for example, to crack RSA 2048, you need around 4,000 logical qubits. So this is not error-corrected, but if you were to error-correct these, you need a lot, I think sometimes 1 million. And so that's kind of the range that you do need just to crack RSA 2048. So not that range. So.
I guess I want to ask the same question about entire resolution. So is the blockchain technology at risk from quantum computing? This is supposed to be Web 3.0. And if you can establish a number of nodes that can collude with each other, it sounds to me like this is a huge risk for the blockchain. You can comment on that?
So my understanding, I've only read one paper written on this, is that the basic hashing protocols are not at risk, but that the particular communication protocols can be. But there is the potential for like quantum secure versions of those protocols, which we hope people would eventually start using. But yeah, there's only really one paper written analyzing that. But as far as we know, like the actual, say, mining of Bitcoin, for example, cannot be sped up. But there's a threat to the kind of communication between different parties. This is my understanding. I'm not an expert. And I should say that Isaac is really one of the world experts on algorithms. He should just be answering almost all of these questions himself. Certainly more than one.
Well, that's the question. So if there's consensus, quantum computers can provide this.
Okay, we have another question in the back.
Yeah. So you won't be able to break encryption.
Can I just also try and answer Isaac's original question? Like, what about the far future where everyone has this? I don't know, and I think an interesting thought experiment is if I took this laptop and I dropped it into 1950, and I dropped one of them in there, and I just, gave it to the US science community, what would they do with it? How would they make their money? How would they fight over it? What would the government do? Probably lock it up to simulate nuclear weapons and so on. But it would take them a long time to realize exactly what they could do with it. And at some level, I feel like this is the kind of world that we're thinking.
Okay, so now I'd like to move on to the more business side of the quantum computing. So my question is this: so from the company's perspective, what kind of expertise do you need aside from quantum computing / quantum mechanics?
I think that should be I'll start. I think there are a couple of things. The very first thing that comes to mind, actually, is a strictly business issue. And it is finding people that are really good at, maybe without saying it pejoratively, really good at sales or building partnerships. Because in fact, if you want to figure out one of the things that Terry alluded to, which is what is this device good for? What sorts of real problems can it solve? Business problems. You have to talk to the R&D groups, the CTO groups at very large companies, and you have to give them enough information so that they can make a decision to make a small bet, a small financial investment in exploring applications and use cases that would allow their companies to benefit from. So interestingly, when I came to the Valley, I did so because I thought, okay, if you want to build a technology company, 95% of the human resource you want in the company are really, really good engineers and scientists. And but what I actually found is that this sales and marketing persona and skill set is really actually quite sophisticated. It's not something that you're going to learn through a PhD program or a postdoc, but the kinds of people that today can go out and motivate through getting someone excited or getting them fearful about applying some scarce resource in their company to exploring quantum computing is really, really valuable. And we, for instance, have someone who came across from IBM, and he himself is a PhD in operations research, so he gets this sort of class of problems, and he was working with Fortune 100, Fortune 200 companies, so he came across to us, and I see this at work every day with him, and he's not really trying to sell. What he's trying to do is to explore a joint development path, an agreement, a collaboration with these companies. So really, at a business level, that's really, really important. Then the other thing that is really important for a software company like ours is something that's not really a quantum computing or quantum information sciences skill set, but it's somewhat related to simply computer science, and it's trying to get the abstractions right to allow enterprise users, users in this quantum in the computing community, to be able to have these tools that will allow them to exploit the power of these machines. And this is not a quantum computing technical skill set, but it's a really valuable skill set. And then the other one that's really valuable, the other thing, is people that understand how quantum processing will be integrated into classical computing workflows. Because really all you're doing, you're taking these existing computing workflows and you're just slotting quantum processing into it to accelerate. You're just shunting off part of the problem, the part of the problem that's really like thorny and taking up a lot of time. So those are a couple of areas. And I think one of the most valuable people going forward for companies like ours, and there will be a lot of companies like ours, will be a CTO that can bridge the quantum engineering group. So those are quantum algorithm people that are developing new algorithms or extending existing algorithms, and the software engineering group that's building the actual product, the cloud product, to bring those two groups together. Because it's a really rare skill. You need someone who's humble enough to work with scientists who need a lot of latitude and a lot of space and a lot of room to explore, but have to be somehow guided towards, hey, this is a business, we have a product we're trying to build. And then these software engineering people who are just machines, are just building something that's going to be launched and turned into a product. To put all those together is really a unique skill. So if you can find someone in the world who really understands quantum information and who has built really heavy-duty systems, like let's say a TensorFlow product, something somewhere kind of in a Google or a Microsoft, something like that. Those kind of people are almost non-existent, but they're going to be really, really valuable. So, and it's a business position ultimately. Yeah.
Yes. Could you speak up a little bit?
Where do you find that marketing and sales is the people who are really astute in quantum computing? Where have you found them?
Well, honestly, when we looked for our person, we looked at all of the big houses like Oracle, just because they have this reputation of being really like hard-nosed people and like aggressive. But we found actually that's not what we want. And so then we had to think, okay, we sort of do want that, but not right now, not in this stage of the evolution of quantum computing. So then we thought, okay, we want someone who's got experience at forging very, very long-term partnerships. So then we looked to the other big software houses like Microsoft, IBM, Google, these groups that do have these long-standing customer relationships and joint development kind of partnerships. So that's where we've looked. So we had to find someone who could stand on their own 2 feet and have a PhD kind of level intellect and technical background. But then someone who's got this this temperament that works well with engineers and scientists, and someone who does have the long game in mind. They're not just trying to book a sale. They understand that the decision-making process inside these big enterprises to engage in something like this is lengthy and thorny, and you might have 30 to 50 people in these big enterprises who have to touch the project before you actually get something funded. So that salesperson, if you want to call it sales, they have to work with all of those people inside the organization. Yeah, but I mean, in our case, we found that unicorn, and he in turn knows a couple other mini unicorns that we're going to bring on board when we scale up a little bit. So yeah.
Okay, thanks, Matt. Any other folks? In that case, I want to move on to the next question. So let's say you're someone who has no experience in quantum computing or quantum mechanics, like 70% of this audience. And let's say you want to get somehow involved with quantum computing, either at a personal level or at a business level. Is there a good resource that you would recommend? Aside from, or is there like a good book or like a class or like something that you personally did that you found useful?
Probably the other ones here.
Oh.
I'll probably answer this because I'm probably the younger one here, but I took a really good class in college that was in computational physics, and I had a great teacher who explained quantum computing. And so that was really my motivation to get into it.
What are you doing?
Won't stay.
Yeah, so really that's what it was. It was a really good teacher who kind of saw the field very early on and saw some scope in it, and inspired us to get into it. And so most of the class, most of the students who were in it, worked on individual projects, and that really taught us quantum computing. And we kind of based everything off the Bible, the textbook of Nielsen and Chang. It's kind of technical, but that really taught us a lot. And I think that was a great avenue for me to get into it. And kind of answering previous question as well, I think, because we're not necessarily selling force and eyes or anything here. It's really tricky to come to clients and deliver this. So our CEO often jokes that even the business development people have all PhDs. And so it's a little tricky, but I think not unattainable. People can get into it. I think there's projects to work on. There's a lot of open source stuff now with IBM and stuff. So a lot of easy projects, a lot of nice projects, like there's musical quantum computing stuff. There's a presentation on that last month. So just to get inspired about it and get into it, I think is key for the younger generation.
So I can speak to this too. I was actually an art major in college. I was a painter by my background. So the way I did it was I just read a lot of technical papers. If you don't want to do that, we do have, like you're saying, some open source resources you can use. So PyQuil is a Python-based version of our instruction set architecture, and you can use that to just run basic experiments and kind of learn the principles of quantum computing. We also have some documentation, some getting started stuff. But if you're a little bit braver and you're willing to go into some more technical literature, Nielsen and Schwang overview of quantum information, quantum computation is really good. There's a lot of literature out there, though. That's very good if you're willing to dive into it.
Yes.
So
example of simulation. If I work in semiconductor simulation every day, things is there like a demonstrable could be a toy example or something like that. It is really good on like a tensor playground or something like that. Just show simulated quantum.
Yeah, so it's a great question. So on our website, I don't think it's there anymore. We had this little game where you could race against a quantum computer, which was just an implementation of a max cut solver that you could try and beat with a better answer. I would say we're now a little bit more focused on kind of more serious applications, but we actually have this open source library called Grove, where we have implementations of real quantum algorithms, but we also have some examples of other things you can do. Just to give a shout out to some other people, I think so. James Wooten, professor at University of Basel, whose goal is to make games for quantum computers. I think his Twitter handle is like Deco Doku or something like that. But he has a great blog where he talks about making the first games for quantum computers. He has a Battleship game. There's another game to benchmark quantum computers where he shows how bad all of the quantum computers are so far. So there are some things out there if you are willing to click around a little bit.
And if I'll get you, but I just wanted to, even though I didn't make Dekodoku, I really want to advertise things because I want to emphasize, if you play this game Dekodoku, you're doing a great service to the quantum computing community, because what you're doing is that if you win this game better than like the best record, you're basically removing the bad noises that are occurring in the quantum computer in better than the best known algorithm to date. And the thing is, I know a bunch of grad students who play this, and there's this like a very generic algorithm that people use, and there are like some grad students who just sees these patterns and somehow outperforms these algorithms, and they have no idea why they're capable of doing that. But if you just play this game sufficiently many times, and if you think you're good, you should just call up James and tell him about your intuition, so that you can help speed up building the quantum computer. Anyway, next question.
I just wanted to share results that found really useful. Peril has a course that's free for everybody to take. So go to the MLT website.
Thank you. All right, so moving on to the next question. The question is, so these days, I meet a lot of undergraduate students or like people outside the quantum computing field, and they ask me, should I go to like quantum computing companies directly instead of going to grad school? Because it used to be the case that the typical route is that you go to grad school, do your study for like 5 years or something, and then you apply for these very specific jobs, and then you end up working on quantum computing. Do you think this is still too early, or do you think this is an actual career path that makes sense?
Just in terms of Rigetti, we offer what's called a junior quantum engineering program for this exact reason. When Chad Rigetti started this company, there weren't actually enough people in kind of quantum information who were willing to go join a startup and kind of actually work on this stuff. And so he started this program to basically train up undergraduate students with degrees in computer science or math or physics, someone with a technical background who has an interest in developing skills and quantum computing in particular. And so our first junior quantum engineering classes kind of graduated to full-time, what we call quantum engineers. Anyone who works on anything from our control electronics to our infrastructure, to our programming languages, to our compilers. So we offer programs for undergraduate students in particular. I would say, with that said, there are, I would say, the graduating JQE classes kind of bifurcated into two, which are the people who have stayed and then people who have gone on to then go to graduate school afterwards, which is also, I think, a very good approach to get some industry experience, to get a little bit of context about kind of what the professional quantum computing world looks like, and then to go into academia and get a chance to really go deep with some things.
there's no other related questions, I want to ask one last question, and then I'll open up for the Q&A. So the last question is this. So the field of quantum computing is still at the beginning stage. Do you think the field has saturated, or do you see still an opportunity in this field that has been not tapped yet?
You're welcome. Okay, I guess I'll say something. So I think the quantum computing. I guess I think there has not been saturation, but I think it's going to open up a little bit in the next few years. So this partially answers some of the earlier questions. So something that I think is going to happen in the next few years, and won't require a breakthrough, is that there's going to be a bunch of people in universities, in companies, who are actually going to construct quantum computers of small to moderate size, up to tens to 100 or so qubits, right? And they're going to want to be doing things with them. Okay? And I think there's an industry that is a mini industry within quantum computing that's about to open up, which is people who have good ideas for what to do on these small scale quantum computers, and can learn to use them properly. Because I think without actually having them around, we don't know how to use them properly. We need to experiment and try things out. So I think this is a mini field within quantum computing, which has not begun yet and is about to begin, and is going to be, I think, a main source of new, fresh ideas and fresh people flowing into the field through that. So that's going to, if you think maybe it's saturated now, it's going to, get a small release valve, at least I think, in that direction.
You mean the availability of these smaller machines that more people can use?
Yeah. So right now there are basically 0 such machines. But in the next few years, we'll hopefully have, I don't know, a dozen machines in the dozens, 50-ish qubits range, or something like that. And people are going to be trying out different implementations, different kinds of hardware, right? And at the level of universities, people will be doing things that are maybe, a little bit different, and then taking those and turning them into startups. That's sort of the pattern. And maybe someone will come along with a breakthrough which really accelerates things. I think what's more likely is we'll just have a bunch of different approaches, each of which will have this kind of small-scale computer available, each of which will be slightly different in its specialization, right? Will be this kind of computer of 50 qubits will be better at doing this kind of task. This kind of computer at 50 qubits will be better doing that kind of task, right? In principle, they could do each other's tasks, but not efficiently and not with the noise. And exploring that landscape of possibility, I think, is going to occupy a lot of people's time in the near future.
Thanks.
Now we will transition into the Q&A session. Thanks for
Before you do that, I just want to remind everybody, these forms you have on here, they're very important to us. It's called Net Promoter Score. The feedback you give us will help us make better events in the future. So before you leave, please fill this out and leave it there. We'll pick it up. Thank you.
So 4 of you raise your hand almost simultaneously. So please don't have any grudge against me. I'll go with you first.
So this is a pretty broad question, but assuming that quantum computers got to a level where they're even like a tenth of what classical computers are today, what do you think we'll start learning about ourselves as like a society, similar to how automation has been driving significant advances through classical computing recently? What sort of societal problems and things about ourselves as a society that quantum computers will expose that you think would be really interesting questions to answer?
sure I like the question. I just feel very, I look at history, the transistor, what was the first use? They asked Vadim, what do you think this transistor is going to be useful for? Oh, you can build it here and there. And they did. And the transistor radio. And, if the future is like Stefan outlined, which I hope it's not, that's the kind of thing we'll do. We'll just sort of, we would be at that point of like, here's some specialized devices that maybe do something. And we would have no concept of the fact that one day we'll build a device that will tell us about global warming. And it's just so far away that once you have a completely new computational power, it just seems really naive for me to even vaguely speculate. I think that we all know what the hard, interesting intellectual challenges are, things like consciousness and so on. But I just think it would be crazy for me to even guess as to all of the other things that will happen once we get to that point where we have the same thing. I think of it as a completely almost orthogonal power to simulate a whole bunch of things that are going on in the world that currently, I think of us as like big thumb monkeys. We just can't deal with the microscopic world. We don't have good intuition for quantum mechanics. It's very difficult to understand, to think about. Quantum computers, I'm hoping, won't have the hang-ups that we have. That we'll build quantum computers that don't care about the interpretation of the wave function. They'll just get on and do quantum mechanics. And at some point they'll look at their kind of monkey masters, as it were, and give us some stuff. But to speculate what that will be, I really don't.
Yeah, there are three of you. You go. Yes, yes.
Just to sort of maybe paraphrase what you said. Maybe the goal is to democratize quantum computing. Things like that's kind of fun. My question is, someone had a first presentation, I forget who was, they were adding about generative and then there was something about adversarial. Is that related to generative adversarial networks or completely different?
Generative learning, so the subclass of classification problems in generative learning. Adversarial circuit learning, it's a separate problem in quantum machine learning.
So it has nothing to do with generative adversarial networks?
No, adversarial circuit learning is, I think, completely separate.
Sorry, the one B.
So,
you'll be
it's
next.
related to the even tips or something for the language that it will be easy to to look at the history of great companies, they were value the same like HP, LTF, and other. We know that. So the logistical question is 4 Kelvin and 10 millikelvin. How do you solve this? This is not going to be solved or bring down significantly. And so I'm looking at quantum Nicholas photons depend upon the temperature. Then it can still be limited to the people who have access to 4 Kelvin.
No, so like there's no reason that if the US government wanted to build a room temperature quantum computer, they would put they put 100 million into the materials for room temperature single photon detectors, and we can have a room temperature. The only reason we're at 4 Kelvin is that the best detectors are at 4 Kelvin, but there's nothing to say that. I mean, it's basically just about growing extremely pure material that you then would have to get into a CMOS line, and we can have a room temperature. In the far future, if you want a room temperature quantum computer, as far as we know, it will be photonic. If you want the fastest possible gate speed, it will be photonic because it's light. But like some people are gambling that, look, for the next 50 years it'll be this, and then it'll be photonic. Some people are gambling for the next 10 years it'll be this, and then it'll be photonic. It will be photonic in the long term. That's the only thing I'm 100% sure about.
Everybody else agree with that?
They don't know enough about photonics, so they can't. I know enough about what they do to know how hard it is.
Yes,
it's sort of true.
Is there a strong national security or defense argument that can be made that the government or DARPA can drive this and do quantum leap through the hand?
Did you mean secretly or?
No, but just for the government to step in and provide the resources. Is there a national defense?
They do.
A national security defense argument that would call for the government to source all these resources?
I can talk about that a bit.
So I don't think you have to consider just defense, national security. I think more broadly, the U.S. government, I mean, that's a subset of it. But more broadly, what the government cares about is national competitiveness. Our government does, just like every other major government in the world. They have the same motivation to be, to expand their leadership in emerging technologies. And so the U.S. government is, in fact, mobilizing kind of belatedly, like governments tend to do. They kind of get on track slowly and then they pick up steam. But the U.S. government is, there's one particular piece of legislation that will mobilize just over $1 billion. It's called the National Quantum Initiative. And I think it made it through the House and now the Senate's going to vote on it. And so it looks like the government agencies that are, for that particular thing, that are going to be driving things forward are the Department of Energy and NIST, and somehow the NSF is kind of going to be involved in that as well. But there's also, attached to that initiative, there's a consortium that's been set up in the U.S. It's called the Quantum Economic Development Consortium. And this is meant to be an industry group primarily that is giving feedback to the U.S. government, and in particular, what kind of enabling technologies need to be invested in and developed so that quantum computing, quantum sensing, quantum communication, so that those quantum technologies can be developed more rapidly. So yeah, so that's happening, yeah. And actually, QC, so that there's actually a governing board that's just been put in place, and the members of that governing board come from the DOE, NIST, Boeing, IBM, Google, Rigetti, and actually QCware as well. And then there's one or two other parties. So there's a 9-member governing board. So both Rigetti and QCware are on that, fortunately. But yeah, that's what's happening.
You mentioned about a lot of this sensing, communications, etc. Those are all signals. The biggest problem for all these systems is related, right? Something background. So, is there anything to use? Like the example was coming from the nitrogen, which is thing. Think about a metal or some kind of metal organic or whatever complex that you can go to reduce the resistance of 10 times. Majority of the whole world's energy loss transmission loss will be formed. Is there anything like that going on?
I think there must be. I mean, there's all kinds of basic research that's. Terry can probably talk about this better than I can, but I think for anybody that's looking at computationally how these kinds of problems can be addressed, the first thing they would look at if they're in quantum computing is what's the mathematical structure of the underlying problem, and is that problem one that's like a bounded error quantum probability, you know, the type of a problem that can provably be solved more efficiently by what? Yeah, but I mean, I'm kind of like this.
So it's a great question. I think we're a ways away from seeing really strong demonstrations of quantum computers being able to solve these problems. With that said, it's a huge area of interest. So almost all of the Department of Energy labs, the NSF, people who are funding academic research that people like Isaac are working on, a lot of it is actually concentrated around things related to energy, high energy physics. So actually, if I could point you to a paper in particular, Oak Ridge National Laboratory it was more on the nuclear physics side, but it's still related to energy. They did an electronic structure calculation of deuterium using our quantum computer and IBM's quantum computer. It's an interesting read, and it kind of shows where people are kind of thinking things might go in energy. But there's a lot of funding in that direction.
And just to add to what Matt was also saying regarding the U.S. involvement, there's also a lot of standardization that's been happening with photography. Most of it's led by NIST and ETSI in Europe. But to set some sort of industry standard and national standard. So those efforts are also taking place. I think just to put a monetary value, I think the NSF DOE kind of, it was $256 million is what they recently announced for just research and quantum projects for science for the data industry.
Sorry, I had a question over there.
Yeah, I have to my graph why the photon quantum computing need a low temperature. Okay? Because you say before SN time, they say 10, right? So what's the difference? Temperature difference, operating
Why
why
do you
the
think
photon one need a low one?
Yeah. Do you want to say? Yeah, yes.
I mean, you know better.
I don't know, but
I'm happy to
speaking all the time.
I'm happy to give a layman's answer. So to operate superconducting qubits, you need to have a superconducting state. So we actually have a circuit that has a junction and some current, and in order to do a gate on it, we apply some microwave RF pulse to it in order to excite the qubit to a different frequency, which is very, very different to the architecture that PsiQuantum is doing, which I'll let Terry speak to. So he was talking a little bit about the operating temperature of some of the detectors. For us, it's actually to ensure a superconducting state of the metal that we're using. So it's aluminum and other metals on silicon. And so in order to get that down to superconducting temperatures, we need to cool it down to that operating temperature.
Operate at a higher temperature, right? You need a
No. So it's
other way around.
Other way around. So you can have detectors that can work at other temperatures. It's just the best detectors work at 4 Kelvin.
10 millikelvin. Yeah.
So 10 millikelvin. Yeah. So much colder. And so for us, the coherence, the lifespan of our qubits actually depend on that temperature. So if we wanted to, let's say, enhance the duration of or the persistence of that quantum state, we would need to go colder in order to basically ensure a more superconducting state or more stable superconducting state. Does that answer your question? Yeah.
Thanks.
I have a question for Matt and those who have tried to raise money from investors, and what kind of feedback and which VCs are friendly to quantum computing industry.
Should I stand up? Yeah. Okay, I'll be really quick because I know we're both done, right?
Yeah. This and one last question.
So first, just general sources of finance for quantum computing for hardware and software. I'll speak to our case first and then more broadly. So in our case, we've received just under $2 million from the National Science Foundation. We've received a little bit of money from, or receiving a little bit of money from the Department of Defense, and we've raised about $8 million from venture capital. And in venture capital in our case are really corporate venture capital firms, so attached to the money's coming from Goldman Sachs, Citigroup, Airbus, one or two others, and then obviously we generate customer revenues. And then more broadly, if you look, really most of the money that's gone into quantum computing so far from venture firms has gone into hardware. And really most of the, well, a decent number of really the top tier firms like Sequoia, Andreessen Horowitz, Founders Fund, have put money into hardware. And so those are really institutional VCs. And the partners at those firms are ones that they're like, they've arrived in life, so they'll take bets like that. They'll take those kinds of risks. And if they're wrong, they don't care if it like dings their career a little bit because they're already there. But most of this risk is the quantum computing is outside of the realm that like someone who's like an up and coming venture capitalist is going to take a meaningful bet on because it's just too risky. So it looks like the real leaders, they're taking the bets. They'll step up first. Yeah.
That's really one last question, but we can ask questions separately after this.
So my question is for Ryan and Matt. So for the quantum computer space on the superconducting bits, and I think there are basically a Josephson junctions, right, which are planar 2D structures. Is there a plan or architecture for maybe stack them up like 3D NAND structures? Because I'm coming from the manufacturing backgrounds, and just looking at the circuitry that Ryan showed us before, there are about 8 circuits or dies, and they're not very scalable in terms of super advanced in terms of like fingerprints. And the silicon wafers can stay away from make a 3D structure, like a 3D and a 3D cross-point structure manufactured by Micron and Hynix.
Yeah, so it's a great question. So it's one of the scaling challenges of superconducting qubits is figuring out how to deliver signals from the third dimension. So it's something we have some, I think, publications on 3D signal integration and some patents on that. So our 16 qubit chip that we're putting online, well, that's online now, it takes signal from just the two dimensions, and when you have 16 qubits, it's not really like you have to really worry about signal delivery and readout lines and stuff like that. But those two challenges, I guess the other challenge that we're working on is signal multiplexing. So right now, if you have a qubit, you want to address its state, you have some big microwave control box that's generating pulses that's going to talk to a particular qubit, right, and read out the state of that qubit. So that obviously doesn't scale, especially not to 1 million qubits, that these, if these boxes cost thousands of dollars each. And so those are kind of the two scaling challenges that I feel confident in saying that we've at least resolved in the intermediate term. So in future architectures, I think beyond the 16 qubit architecture, we'll be delivering signal via, I don't know if I can say, but from the third dimension, I'll just say.
You want to get yelled at?
Thank you, Ryan. So we're out of time, and so as I said, if you have extra questions, some of us will be around, so you can talk us. Before we conclude, I just wanted to thank all the panelists/speakers for coming over. It was a great time. Let's just give them a round of applause. Also, importantly, none of this would have been possible without Nathan, Nikki, Henry, and also Deutschbank who provided the food. So,
please fill out the form. Henry, 1 minute. It's gonna.
1 minute.
Sorry.
Before we leave, let me summarize the program. Thank you for coming to the California Software Professional Association, CSPA.com. We are a nonprofit 501c3, so your donation is tax deductible. Anything I can do for you, let me know. I'll be around outside. Thank you.
Okay, thank you.
Still another speech?
What do you want?
No, I just have a few questions. Go for it. That's not so sorry.
I send you an email with some.
Yeah, that'd be great.
Yeah, I just sent you. It's on
Great.
So you can take a look at it.
Appreciate it. I like that. The deep learning, man. That's really good. I put that on my last on my paper.
Really interesting stuff. They talk about deep learning.
Yeah, they have to because I'm disappointed. The not in their presentations are great. This